Dear students, this is our eighth lecture on stereochemistry and fourth lecture on asymmetric synthesis. As I have told you in our previous lectures that asymmetric synthesis is basically a reaction in which an achiral compound undergoes a chemical reaction to produce a chiral product. And the stereoisomers which are formed during the reaction, they are formed in unequal amount, so that the product formed is asymmetric in nature. And some of the common reactions which take place in case of asymmetric synthesis may be reduction of carbonyl compounds, then oxidation followed by hydroxylation of alkenes can lead to the formation of asymmetric centers in the achiral alkenes. Similarly, Grignard reaction can also lead to the synthesis of uh, asymmetric alcohols. Then hydroboration oxidation and aldol condensation. These are some of the very common reactions which can use asymmetric synthesis for production of chiral compounds. As far as asymmetric synthesis is concerned, it may be of two types, that is partial asymmetric synthesis or absolute asymmetric synthesis, which we have studied in case of our second lecture on asymmetric synthesis. And then in the third lecture on asymmetric synthesis, we have discussed about first generation methods, that how a chiral substrate can be used for the partial asymmetric synthesis. Now, in the present lecture, that is the fourth lecture on asymmetric synthesis, we will be discussing how a chiral auxiliary can be used for the asymmetric synthesis. And these types of methods where we are using chiral auxiliary for the asymmetric synthesis, they are called as second generation methods. Now, chiral auxiliary is basically a chiral intermediate which where this auxiliary is attached to a chiral substance to give us a chiral intermediate, and that chiral intermediate will be converted into a chiral product through asymmetric synthesis, and ultimately the asymmetric product is formed by removal of the chiral auxiliary. And most common among these types of methods for the asymmetric compounds is chelation informed chirality transferred with nitrogen derivatives. And these nitrogen derivatives, they may be chiral amines, amides, amides, sultams, and other nitrogen based chiral auxiliaries which can be used. And these are formed from the reaction of ketones or carboxylic acids that will react with these nitrogen based compounds to give us a chiral auxiliary, and that will undergo a reaction to produce asymmetric compounds. And among these chiral auxiliaries, these are some of the important commonly used chiral auxiliaries for asymmetric synthesis. First is proline or prolinol based chiral auxiliaries. These are the most commonly used chiral auxiliaries for asymmetric synthesis. Then amide systems, they can be used. Then enamines, chiral hydrazones, oxazolene systems, they are used as chiral auxiliaries. Then acyl sultan type of systems, they are synthesized from sultam or their derivatives. then chiral acyl iron complexes, then chiral enolates. They can be used in double asymmetric synthesis like aldol condensation. So these are some of the commonly used chiral auxiliaries for asymmetric synthesis of different types of compounds. So first category is prolinol based chiral auxiliaries. These are used for synthesis of various types of chiral organic compounds, and most common among these is alkylation of carboxylic acids. So these types of chiral auxiliaries, they were first used by Evans and Tachus, and they demonstrated that diastereoselective alkylation of uh, carboxylic acids can take place through metal ion chelation based mechanism, and generally they used lithium enolates which were derived from prolinol type chiral auxiliary for the synthesis of alpha substituted carboxylic acids which were chiral in nature. So basically what they have done is they synthesized these types of prolinol based chiral auxiliaries. The prolinol on reaction with either carboxylic acid derivative, carboxylic acids or their derivatives will give us these types of prolinol amides, and these amides on reaction with a strong base like lithium diisopropylamide, we know that lithium diisopropylamide will react with this amide. This carbon is having alpha hydrogen and carbanion will be generated. This will be converted into an enolate of this type. And then these enolates, when they are reacted with alkyl halides, they will undergo alkylation at this carbon, and we will see that this alkylation is an asymmetric alkylation because these enolates, they can undergo alkylation either from C phase or from RE phase of the enolate. So if we are having prolinol based enolate, then generally the alkylation occur preferentially from the C phase of the enolate. Whereas if we are having substituted prolinol, that this hydrogen is replaced by alkyl group, then generally RE phase of the enolate undergoes alkylation reaction. So that means depending upon the substitution at this oxygen moiety, we can have a different type of enantiomer of the carboxylic acid formed after alkylation reaction. So this chiral intermediate which is formed after the alkylation, when it undergoes hydrolysis, we will get alpha substituted carboxylic acids as the product, and uh, in these types of chiral auxiliary, we will get one enantiomer of the carboxylic acid, whereas in these types of chiral auxiliary, we will get the other enantiomer of the alpha substituted carboxylic acid. So, by choosing the type of enolate, we can synthesize different enantiomers of the alkylated carboxylic acids. So this is how we can convert achiral carboxylic acids into chiral alpha substituted chiral carboxylic acids. Then another method for alkylation of carboxylic acid is that we can use a different types of chiral prolinol auxiliaries. So basically for using a different prolinol based chiral auxiliaries, because the chiral auxiliary which we have seen in the previous method, this cannot be easily recovered from the reaction mixture because it is highly soluble in water. So to overcome this problem, a new type of chiral auxiliary is synthesized from L-proline. So when L-proline undergoes a esterification, the corresponding ester, methyl ester, will be formed when it is reacted with methanol, and then on reaction with the acid chloride derivative, this will be converted into this type of amide. Then we know the esters, they react with methyl magnesium bromide, or under Grignard reaction they will be converted into the, after hydrolysis, into these types of tertiary butyl alcohols or tertiary alcohols. So this tertiary alcohol based chiral auxiliary then undergo a similar reaction which we have done in the previous case. First, this will generate an enolate in the presence of lithium diisopropylamide, and then that enolate will react with the alkyl halide to undergo alkylation reaction. So both the enantiomers, they will be formed, but because the reaction is preferred at one of the phases, that is Z phase or RE phase more, so one of the enantiomer is formed in more amount and other is formed in less amount. So here if we start with this type of chiral auxiliary, we will get R 2-methyl butanoic acid or R alpha substituted carboxylic acids as the major products. So this is how we can have asymmetric carboxylic acids from these types of chiral auxiliaries. Then another method which is also used for alkylation of carboxylic acid is use of chiral auxiliaries which are having C2 symmetry, and these are mostly pyrrolidine derivatives. They, you can see that here an additional hydroxyl group is there if we compare these with prolinol based chiral auxiliary. So these types of pyrrolidine based chiral auxiliaries, they will first be converted into the corresponding amides, and then these amides will give us enolates in the similar manner, that is lithium diisopropylamide will react to create this enolates, and then these enolates, they will undergo reaction in alkylation reaction in a similar manner. And here, depending upon the type of chiral auxiliary which we will use, either this RR chiral auxiliary, or if we reverse these positions, then this will be converted into its enantiomer, that is 2s5s chiral auxiliary. So either 2R or 2s chiral auxiliary, they will react with the strong base, that is lithium diisopropylamide, to give us enolates in the same manner. So here the Z enolate will be formed in this case, and this Z enolate will prefer to be attacked by the alkyl halide through acid phase. And if we will use R chiral auxiliary, then the product formed will be R substituted carboxylic acid. If we will use S chiral auxiliary, we will get S substituted carboxylic acids as the product. So we can see, for example, here when we are using the R chiral auxiliary, then we will get the Z inlet, and that Z inlet will give us this intermediate, and which on hydrolysis will give you R2 methyl butanoic acid as the major product. So reaction proceeds with high anisio selectivity in such type of conversions. Then is we can also synthesize alpha hydroxy carboxylic acids through asymmetric synthesis, and this in this case the chiral auxiliaries derived from S-proline, they are used for such type of conversions. So when S-proline is reacted with alpha beta unsaturated carboxylic acid derivatives, for example, here in this case, we are using alpha beta unsaturated carboxylic acid chloride as the starting material. So this acid chloride will react with this amine to form this type of amide based chiral auxiliary derived from S-proline, and then this chiral auxiliary reacts with N-bromosuccinamide. You know that N-bromosuccinamide will be used for bromination of this carbon-carbon double bond, and this type of bromonium ion will be formed, and then the nucleophilic attack of this oxygen will take place at this carbon to open this ring, and we will get the lactonization of this part of the molecule, and this type of lactone will be formed, and bromine will go to this position. So basically through N-bromosuccinamide we will prepare these types of bromolactones, and these bromolactones, they undergo reduction in presence of tributyl hydride. So alkyl halides, they are converted into alkanes through these types of reduction reactions. So this Br will be replaced by H tributyl bromide will be formed, and this H will go to the place of bromogroup, and this on hydrolysis. So hydrolysis will take place. One is at this place, hydrolysis of this nitrogen carbon bond, amide bond will take place. So here you will get carboxylic acid, and then hydrolysis of this carbo ester group will take place, and here this bond will break, OH will get attached to this, so there H will get attached, and L S proline will be generated back, and rest of the molecule you can see here you will get carboxylic acid, and here you will get hydroxy group. So alpha hydroxy carboxylic acids which are asymmetric in nature, they will be formed. So this is how asymmetric synthesis of alpha hydroxy carboxylic acid can be achieved from alpha beta unsaturated carboxylic acids. Then similarly alkylation of carboxylic acids or aldol condensation can be achieved through oxazolidine derivatives, and these are also known as Evans reagent. So this oxazolidine derivatives, they depending upon the type of substitution which is present at this C4. So here you can see that this is a alpha bond, whereas here it is a beta bond. So depending upon the stereoselectivity at this carbon, you will get the type of product formed in these types of chiral auxiliary. So the method is same. The first is enolization of this metal based enolization, and then alkylation will lead to these types of chiral intermediates, and these chiral intermediates on hydrolysis will lead to the formation of alkylated carboxylic acids as the product. and the configuration of the products form will depend upon the configuration at this carbon, that is whether if it is alpha or it is beta, we will get different enantiomers of the products formed in these cases. Then hydrolysis of these types of uh, chiral intermediates can lead to the formation of carboxylic acid, and similarly if we reduce these with reducing agents, then this will lead to the formation of the corresponding alcohols as the product. So either alcohols or substituted carboxylic acids or substituted hydroxyl compounds, they can be achieved through these types of asymmetric synthesis reactions. Then you have seen that chiral auxiliary which we have used in the previous method, that is very expensive and its synthesis is very difficult. So for that purpose, this chiral auxiliary has been modified. Chiral auxiliary has been synthesized by Evans from asphylene. So first this undergoes alkylation, N-alkylation at this place, and then this N-alkylated product in the presence of uh, hydroboration reaction undergoes reduction of this carboxylic acid into alcohol, and then this undergoes cyclization to give us these types of oxazolidine derivatives, and these oxazolidine derivatives they act as chiral auxiliaries for synthesis of different types of substituted carboxylic acids or alcohols. Then chiral enamine systems, they can also be used for the synthesis of different type of asymmetric alkylated products, and most commonly these types of systems they are used for alkylation of ketones. So these types of chiral cyclohexanonamines, they can generate enamines at any of these carbons. These are symmetrical carbons. So enamines can be generated when these are reacted with strong bases like lithium diisopropylamide. So when lithium diisopropylamide reacts with these types of chiral cyclohexanonamines, they are converted into enamines. And these enamine derivatives then undergo alkylation in a diastereoselective manner to produce optically active alpha substituted ketones as the product. And depending upon this R, if this R is methyl, the enantioselectivity is 82% in this case, enantiomeric excess. And if it is a bigger group like N isopropyl, the diastereoselectivity or enantioselectivity increases to the order of 95%. So likewise, after hydrolysis of the chiral auxiliary intermediate, we will get alkylated product. Similarly, if we are having this type of chiral cyclohexanonamine, then on reaction with LDA, the enamine will be formed. This will become double bond and lithium will get attached to this nitrogen, and this type of metal mediated enamine will be formed. Then this enamine will undergo alkylation reaction at the alpha position, followed by hydrolysis will lead to the formation of these types of alpha substituted product. So depending upon the configuration over here, we will get the R or S enantiomers in these types of product. And similarly, depending upon the type of size of this R group, we will get the selectivity in these types of product formation. The bigger the group at this R, bigger the R group, higher will be the selectivity. So basically, the diastereoselectivity in alkylation in these types of enamine derivative can be explained through this mechanism. So here this structure is more stable in comparison to this because this will lead to the formation of this type of R product. So R product is formed more because this structure is more stable in comparison to this structure. So that is why the major product formed in these types of chiral auxiliaries will be the R product, and similarly if the other type of enamine structure is formed, then that product will be formed as the major product. Then hydrazone system can also be used for alkylation of ketones. Here basically what happens is that methylated dimethyl hydrozones they have been found to be highly reactive intermediates in either regioselective asymmetric synthesis or diastereoselective asymmetric synthesis, where a new carbon-carbon bond formation takes place. And all these reactions they are mostly electrophilic substitution reactions which take place at the alpha carbon to the carbonyl. So here what happens is if we are having an achiral ketone and we react this with a chiral hydrazone, what we will get is a chiral enolate equivalent formed. And when this chiral enolate undergoes metallation, this hydrogen will be placed through electrophilic substitution by metal ion, and then this metal will be replaced by the electrophile, leading to the formation of on hydrolysis it will be converted into a chiral alpha substituted ketone. So we can see that how these achiral ketones they are alkylated to give us a chiral product. And the advantages of this type of methodology is that these hydrozones they which are prepared from chiral hydrazines, they can be easily prepared, and even the sterically hindered ketones they can also be used for synthesis of these types of chiral enolate equivalents. And these hydrozones which are formed, they are highly stable, and their metal derivatives which are formed on metallation from these enolate equivalents, they are also highly reactive in nature, and the subsequent electrophilic substitution takes place at a very faster rate and gives a very good yield. And then the removal of this moiety is very easy, and it can be done by many methods to give us a final chiral alkylated product. Now the hydrazone methods they generally use SAMP and its an isomer, that is ramp S1-amino 2-methoxy methyl pyrrolidine as the chiral auxiliary. So this is SAP. This is derived from S-proline. First S-proline undergoes reduction with lithium aluminium hydride, and this is converted into the corresponding nitroso prolinol derivative, and this on reaction with sodium hydride reduction followed by alkylation will lead to the formation of this SAM having S configuration. So we can use SAM, or similarly if we start with R proline we will get it's an isomer, that is RAM will be synthesized. So S proline will give you SAM and R proline will give you RAM as the chiral auxiliary. So depending upon the starting chiral auxiliary, we will get the type of product which is alkylated product. So one example is synthesis of optically active S4-methyl 3-heptanone. This can be synthesized from pentane 3-one, which is optically inactive, and alkylation through use of SAMP as chiral auxiliary will lead to the formation of S product. So if we will use RAM, then we will get R4-methyl 3-heptanone as the product. So first is that this ketone reacts with this amino group to form this type of hydrazone. So SAMP hydrazone is formed, then this SAMP hydrazone will react with LDA, lithium diisopropylamide, and the corresponding enolate will be formed at this place, and this enolate then will undergo alkylation reaction to give us. So all these are the isomers which are possible through alkylation, and out of these four, this is the major product which is formed during the reaction. So ZSS isomer is formed as the major product which will lead to the formation of S product. Similarly, if we will use R, then this uh, this R isomer will be the major product, and this will lead to the formation of R product. Then these hydrogens or SAMP or RAM, they can also be used for the synthesis of alpha hydroxy carbonyl compounds. So instead of alkylation, alpha hydroxylation can be there for conversion of ketones into alpha hydroxy ketones. So here also first we will get the SAMP hydrogens from the reaction of ketone with the SAMP, and then this SAMP will react with lithium diisopropyl amide, and a enamine will be formed, and this enamine hydrazone will then react with 2-phenyl sulfonyl 3-phenyl oxaziridine, and opening of the ring will lead to the formation of this type of alpha hydroxy SAMP hydrazone. They will be formed, and then this will undergo oxidative cleavage at this point to give us alpha hydroxy ketones, and this moiety will be released from the reaction, and this will further undergo reduction to convert this nitroso into amino group, and this can be released. And the products with alpha hydroxy ketones, which are asymmetric product, they are formed from 89 to 96% ratio selectivity depending upon the R alkyl group present at the ketone. So these are some of the common applications of SAMP or RAM for the synthesis of different type of asymmetric organic compounds. We can synthesize alpha substituted acyclic ketones through these types of reactions. or we can synthesize alpha substituted cyclic ketones which are asymmetric in nature using uh, these types of chiral hydrazone or chiral auxiliary. Then aldol condensation can lead to formation of beta hydroxy products of this type. Then we can synthesize beta ketoesters again through condensation reactions. Then alpha beta chiral amines, they can be synthesized. Then beta chiral amines, they can be synthesized. Then alpha chiral amines can be synthesized. Then alpha substituted acyclic aldehydes can be synthesized. And this group may be alkyl group or hydroxyl group as we have seen. So these ramp or SAMP hydrozones as chiral auxiliary can lead to the formation of many types of asymmetric organic compounds. So this is all about this lecture, and these are the references which have been used for preparing this lecture. Thank you very much.